Hi, the topic this week is dynamic programming, which is something that you've done before in Com 25 or Com 2010. So, 4 weeks of Com 3010, and every week we're just doing something that you've done before. Well, I hope you can at least appreciate that we are going a bit deeper every time, and this time will be no exception. I think in Com 25 you only spent a week doing dynamic programming, and that's pretty early on, like week 3. And at that point, I don't think you can appreciate the topic yet. So I usually say this is the hardest topic in Com 25, but you just didn't do much of it. I'm not sure if they even ask you to write a dynamic programming algorithm, for example. All right. You don't have to design your own dynamic programming algorithm. So I'm going to review dynamic programming again. This is what this lecture is about. Just review what you've done in Com 25. We're also going to talk about overlapping subproblems, which is why you can use dynamic programming in this lecture. In the next one, I'll talk about optimal substructure, which is actually in Com 5. Apparently, it was mentioned there. I don't know if you remember what optimal substructure is. And we'll do some examples. Yeah, that's pretty much what we're going to do this week with dynamic programming. So for this week's topic, it will also be good if you give the textbook a read, like CLRS chapter 15. I'm going to follow that very closely, and I feel like with these slides, it's like I'm just explaining the textbook to you. So, yep, be great if you also read the textbook. Okay, so what is dynamic programming? I want to go back a bit to brute force, which is what we did last week. And I hope you're okay with the idea of breaking problems into subproblems. That's pretty much what we did last week, right? So, and like the example here, we have the original problem on the root, and then every children is just a subproblem. So I kind of like talking about brute force because it feels pure, like this tree here. These are just all the possible answers that I can generate, right? And I have to go through all these possibilities and work out which one's the correct one. No shortcuts, no smart techniques, just generate everything and go through everything. Of course, the problem is the complexity. So with this tree here, the number of subproblems you're gonna have is gonna be exponential because every node you branch out to two different nodes. All right, that's exponential. And with dynamic programming, well, first thing about dynamic programming is there's nothing dynamic about it. They call it dynamic because it sounds catchy. Like seriously, go look it up on Wikipedia. They were hoping to get some research funding or something, and then if we call it dynamic, they say, or we call it dynamic, it's gonna sound sexy, and we're gonna get money from there. So that's why it's called dynamic. There's nothing dynamic about it, and it's actually very simple. So some problems will have subproblems that overlap. What do I mean by overlap? Well, suppose you're at the top of the tree here, at the root, right? That's your original problem. And then you can break it down into two smaller subproblems, going to the left and going to the right. What if I break this down further and I have the subproblems, let's say this one here on the right. What if that is the same with the subproblem if you go to the right and then go to the left? So these two, they're the same. So the idea is, this problem is actually not that complicated after all, because if I go left and right, that's the same as me going right and then left. So if I can recognize that they're actually the same, okay, I can merge the nodes together. And what I mean by merging them together, for every subproblem, I will only do it once. So I'll do it once, I'll compute this subproblem, and then I'll store it somewhere. So if I ever come across that same subproblem again, I will just look at what I stored before, because I already have the result. Basically, you avoid doing the same computation again and again and again, because that would be a waste. This is very easy to see with Fibonacci. Again, Fibonacci, something you've seen in first year, second year, third year. Why do you always see Fibonacci? Because this is the best way, this is the best example to explain how dynamic programming works. Right? Because if you try to compute Fibonacci using recursion, right? right? And we always say this is bad. This will take forever, because this is what the search tree looked like. So if you want to compute Fibonacci 10, you have to work out Fibonacci 9 and Fibonacci 8. If you want to work out Fibonacci 9, you gotta work out Fibonacci 8 and Fibonacci 7. And you want to work out 8, you gotta work out 7 and 6. So look at how many times you have to compute 6, for example. Once here, twice, 3 times, 4 times, 5 times. You have to compute 5 times. You have to compute 5 even more than that, right? You're doing the same computation again and again and again and again. And if you're doing it like this, recursively, well, this tree kind of looks similar to the one we had before, right? So it's going to be 2 to the n. Well, actually, this is going to be better than 2 to the n, slightly better, because it's going to be longer on one side than the other. But it's still a pretty bad complexity, like something to the power of n. It's still exponential. So if I try to run this code, this is what happens. So n equal to 10, Fibonacci of 10 is 55. I have to do 100 recursive calls. N equal to 20, I gotta do 13,000 recursive call. N equal to 50, I gotta do 25 billion recursive call. And this is actually, if I put a column here with 1.62 to the power of n, you can see how it's pretty close to the number of recursive calls you have to make. But yeah, this is an example where, well, you don't do it using recursive calls. You don't do it using recursion, I mean. You do it using dynamic programming. Very simple idea. So I'm gonna start at Fibonacci 10, going down to 9, 8, 7, 6, and this will go on until you hit 1, right? But then you backtrack up to 2, up to 3, up to 4, and then those values, for all of them, you store inside a table. That's what I'm doing here on line 6 here. So when I have to go to the right subtree on any subproblem, if I go to the right subtree, let's say from fib 7, I have to work out fib 5, when I would have done it, because I've done fib 5 down here, right? If I have to work out fib 8, I have to work out fib 6. Well, I've done fib 6. By the time I backtrack to fib 8, I already have the value fib 6 stored inside the table. I can just use that. So how many function calls do I have to make? Well, it's just linear. It's just one line here. Because so every time I go to the right, I just want to make one call and I'm done. You can't even do better. Since really all you're doing is constructing this table here, right? These are the list of Fibonacci number. Is this exactly the array table that I'm making there? Then you can do this bottom up. So bottom up means that I will start from the beginning of table. You see that if I'm doing top down, all right, I'm going to start with n equal to 10, for example, the largest value. I keep on reducing it, and I will fill up. Well, I'll try to fill up the table from the end, but I'll end up filling the table from the left anyway. And then we say, well, if we're going to be doing that anyway, so why not just fill up the table from the left from the beginning? Use a for loop. And I will say that if you can do something using a for loop, then go use a for loop, because if you call a recursive function, whenever you do recursion, it costs extra. You have some overhead, so you have to pay. So it's always good if you can do for loop. And this is what we call the bottom-up dynamic programming. So top-down, we call that memoization. Bottom-up, we call that tabulation, because you put it inside a table. Well, you put both in the table anyway, but that's just the name that they use, memoization and tabulation. But yeah, if I have this table here, I don't have to deal with the whole tree, right? I'll be removing a lot of the subproblems, because I don't need to go through them again. I can just look at the table. But remember that dynamic programming, in a way, this is still brute force. You're still, it's still kind of brute force, because you're still generating all the possible cases. It's just that you also realize that some of them overlap. So you still going through all possible cases, but whenever you hit a case, you store it. So if you ever have to use that again, you can just do a table lookup. Right? Now, the second dynamic programming problem that you did in Competitive 5, I'm guessing is the longest common subsequence. Like I remember, in the workshop, there's always a lot of dynamic programming questions, and as a tutor, I would just say, this is way too hard. I don't want to do this. So I don't know how many dynamic programming questions you went through, but at very least, you would have seen longest common subsequence. This is the example they always use in Competitive 5. So what is longest common subsequence? Just to refresh your memory, I give you two sequences, X and Y. Well, let's say this the GTA to the Gattaca. This is like a DNA sequence, right? I give you two sequences, and you got to find the common subsequence. In this example here, I bet you can't work that out. That you can actually find the string ACATGATACG there, right? That's the longest common subsequence. It is actually used in biology. They do this like with the DNA sequencing. I put up the code for longest common subsequence on my GitHub. You can also see a visualization of the algorithm in this link here. If you remember in Competitive 5, there's a website where you can see P3 animation and all that. That's the same website. It's a very good website. You can see the visualization of a lot of algorithms. But anyway, longest common subsequence. How do you actually do this? Well, let's use a small example. Let's use TTA, CAT, and TAG, TTG. And we're going to find the longest common subsequence in this. Maybe you can try to work out what the answer is. There are actually two answers, GTT and TAT. See if you can spot it. For the example here, I'm going to derive the answer TAT, so just think that TAT is going to be the answer. Let's go through it. Now, you don't have to remember what you did in Competitive 5. We talk about a way to do this efficiently in Competitive 5. Don't have to worry about that. We'll go through it again if you forgot how to do it. But most importantly, try to solve this using brute force. Because I said in the meme earlier, right, that dynamic programming is just brute force. It is. Like you're trying to find overlapping subproblems. You still generate all the possible solutions, right? You generate all of them, but then as you go through them, you realize, well, if I'm going down this path, I have computed this before. I don't need to recompute this part again, right? You still try to go through everything, but you also realize that I might be going through the same thing twice. So let's store that somewhere. Now, if I tell you that these are two strings here, you got to find the common subsequence, and you want to brute force it, how would you do it? Okay, so you start with both strings. All right, so you try to match them. You try to match them from left to right. I'm thinking, all right, that G there doesn't do nothing, so I'm gonna get rid of it. Then I match TA and TA. Cool. I got TA as an answer. And then what happens? All right, I'm gonna get rid of the C. Doesn't do much. Get rid of the A. Doesn't do much. Get rid of the T. Well, I'm stuck now. I got nothing else. So what do I do? Well, actually, there's a T there. So what I do is, all right, let's me get rid of the G. Now I found a T. They match. Cool. So I found TAT as the answer. I mean, give this a try. Give this a try. Try to see if you can get the other answer like GTT. But with this one here, there's nothing left, right? I get rid of the T, I get rid of the G, and that's it. So that's my answer, TAT. So that's how you do brute force on this one. I mean, this is what's that's what's running in my head as I do this. And sometimes the hard thing about dynamic programming is same thing with brute force. Like, how do I break down my problem into different subproblems? Because if I can't break down my problem into different subproblems, I won't be able to do it, not even using brute force. And this is what makes dynamic programming hard. Once you know how to break it down, like, it will be easy for you to work out the overlapping subproblems, and there's nothing left to it. You just store that somewhere. Now, I hope you can see that this is kind of what we did with the at least this was my train of thought when I was doing the problem before. So I will have the full strings here. Then I will say that I'll look at the leftmost character and do they match? Well, they don't match. So if they don't match, I actually got two options now. Either I drop the G and I go to this right subtree, or I drop the T and I go to the left subtree. Right? And then what? Just keep on doing the same thing. So the rule is, if I go left, I'm going to take away one character from the beginning of the bottom string. If I go right, I'm going to take away one character from the beginning of the top string. Well, but there's a but. Well, if I'm going left here, that's exactly what I'm doing, right? Go left, reduce the lower one. Go right, reduce the top one. But if I see a TACAT and I see a TAGTTG on the right subtree here, well, these two match. So I gotta do something special here. I'm just going to take the matching character. That's the T and the T here. So I'm gonna end up with ACAT and AGTTGT. So I'm doing something slightly different. Another thing you should notice from this node here, if I go right, meaning I take away the character from the top string, I will end up with this case as well. So there's like an overlap here, right? And also, different branches give me a different answer. If I go left here, I'll get GT. Actually, if I go left here, I'll get GTT as an answer, not GT, sorry. So, well, on this left here, at least you can see there's a matching GT. If you go further down, you're going to see that's a GTT. If I go down this branch here, I will get AT as an answer. Like, you can confirm that this is the matching would be A and then T. There's nothing else. And if I go down this branch down here, I'm going to have TAT as an answer. Right, going down different branches gives you different answers. This is what it looks like. If you only care about one case, you got three possibilities. That's what I've been doing in the previous diagram, previous tree. You start with the full strings. If I go left, I take away the first character from the bottom one. I take away Y1. If I go right, I take away X1. So X1, X2, X3, these are just the characters. Or if I go down, I take away both of the first characters. So this will only happen if X1 matches Y1. So this is the general algorithm for longest common subsequence. But hopefully you can see that now we have overlapping subproblems. Right? Because if I go left and then go right, that's the same as me going right and then go left, the same as me going from the top to the bottom. Like, confirm yourself. Make sure you know what's going on here. I can go further down, like this. These two matches again. So there's a lot of overlapping subproblems. So this is like the diagram I had at the beginning, when instead of 2 to the n, I have something much better than 2 to the n. So hopefully remember doing this in COM 2 to 5, you had to fill up a double array, right? And that's because I can rotate that like that. And you will see, I can represent the problems and subproblems with this kind of structure, which is just a 2D array. And that's what you did in Comp to the 5. Okay, example. Let's say your substring is AT and TG. This is like one part of it, like, right? If your string is AT and TG, then either you, well, if I go right here, I take away A, so I got T and G. If I go down, I got AT versus G, right? If I go diagonal, I got T and G. Well, actually, these are the breakdowns of the problems here. But because you're not going to, the way it's done here, you're going to start from the bottom, actually. What is it saying? If I got empty string and empty string, then the number of matching characters is 0. If I got empty string and G, the number of matching characters is 0. If I got empty string and TG, the number of characters is 0. So when you break down the problem into smaller and smaller and smaller subproblems, right, you're going to hit the limit where it's either like one string is empty and the other string still has something in it. And in that case, everything the answer is just going to be 0 because you can't match anything. There's no subsequence to match. Now, once you worked out all these edge cases, well, should I call edge cases? Yeah, like the base cases, maybe that's a better word. Once you work out all the base cases, you can work out this guy here. You can work out this TG case. What do I mean with the arrows here? Well, if you have the string T and the string G, they don't match, right? So you get two options. Either you remove T and you see like what am I gonna get in return, or you remove G and you work out what you're gonna get in return. Like you try these two different cases. So you break it down into small subproblem, go down, I'll go to the right, and then you go back. You pick which one gives you the better answer. Now, if you want to do something like this one here, if you have the case T and TG, they actually match. So what you know is you got one answer, you got one character which are the same. So if you pick that character because of the match, then your next case is going to be empty string and G because you moved T from both, right? That's what happens when there's a match. So you just follow these two rules. If there's a match, you do 1 plus the diagonal because you just match one extra character. If you don't have a match, you just take the maximum of the right or the bottom because you know that this character here will not make any difference. So maybe play around with this a bit. But this is the table that you did in Comp to the 5, right? And you start with all these the base cases where you have an empty string and something else, and then you fill it upwards. So try to use the logic that I explained to you. For example, where can we find a good example here? How about this cell here? So this corresponds to ACAT and GTTG. Okay, so the first character is A and G. Well, A doesn't match with G, right? So you're not going to get a match from that character. So now, what do? Well, I have two options. I'm going to remove G, right? Or I'm going to remove A. So if I remove G, I'll go down to this this cell here with the value 1. I'll be comparing TTG and ACAT. If I remove A, I'll be going to the right. This one here. I'll be comparing CAT and GTG. So hopefully you can see that these are just subproblems of doing ACAT and GTTG. All right. So now what happened? Both ways, if I go to either way, I'm gonna get a 1, right? Because that's the maximum that I get. Now that is different on this case here. Once I fill up a 1 here on ACAT, TACAT and GTD different because if I remove G and go down, I'll actually get 2 as an answer. If I do the same problem with TTG and TACAT, I'm gonna get the answer 2. So I just take the maximum of these two. Right. So I have a problem. I can branch to 2 different subproblems, right? And let's say the subproblem on my left is telling me, hey, if you do that, you're gonna get 2 matching two matching characters. If you remove this character, you're gonna get two matching examples. And the one on the right is telling me if you remove that character, you're gonna get one matching character, one matching example. So which one do I take? I take the maximum one. I take 2. So every cell, I just take the maximum. And same, go on. If the character is actually the same, like this one here, T matches that T, then I'm going to lop them off, like get rid of them, and then I will jump diagonally. Because if I take away both T's, the next case I'm going to be doing is going to be comparing ACAT and AGTTG, right? So I should go down. I should do 1 plus what's there, that 2 there. And look, knowing how this algorithm works is good. It would be great if you know how this works. But most importantly, make sure you understand the whole idea of overlapping subproblems, which I think is easy to see here, right? But you gotta go back to the trees that I drew earlier, right? And this one here is actually a bottom-up example. You can also do this using top-down approach. You can, but basically whatever DP you can do, we can always use top-down. Top-down is easy, right? So you just use recursion. You hit a case from the top, so your problem becomes smaller. Every time you hit a case, when you know the answer, you put inside the table. That's actually not that difficult to do. Top down is generally easy-ish to do. Bottom up is the one that's harder. This table here, this is bottom up. How do you come up with this? That's harder. You gotta recognize what the base cases are, and you actually work from the base cases to go your way up. That's harder. And what we're gonna be doing in this unit, we're gonna be doing both. We're gonna be in top down. We're gonna be in bottom up. And you will realize that the bottom-up approaches sometimes is one that you go, how on earth did they come up with this sometimes? Right? You gotta wonder, and how did they come up with this? So, yep, we're gonna go to them. I think that should be enough for this lecture. It's a pretty easy one, right? It's just a revision of COM 2-5. And I'm probably explaining that way too well, way too slow. So sorry if you think this is boring, but hopefully that's a good start. All right, we're gonna go to the next topic in the next lecture.